Welcome to section 10.2, two-dimensional vector practice. At the end of this section, we should be able to answer all of these questions. What is a vector quantity? What is a scalar quantity? What is a vector? What do the tail and head of a vector represent, and how do we distinguish them? What is the magnitude of a vector, and what are the other terms we use for this concept? What is a unit vector? How do we calculate a unit vector in the direction of a given vector? What is required for two vectors to be equal? What does it mean to translate a vector? What is the opposite of a vector, and how do we symbolize this new vector? What is a position vector? What is a displacement vector? How do we denote a vector sum? How do we draw the resultant of a vector sum? How do we denote a vector difference? And finally, how do we draw the resultant of a vector difference? Let's review some vocabulary. A vector quantity has both magnitude and direction. For example, force, velocity, and displacement. A scalar quantity, on the other hand, has quantity but no direction. Time, speed, volume. A vector is a directed line segment that represents a vector quantity, and we symbolize that vector with a little arrow above our variable. The head of a vector is where the vector ends, and the tail of a vector is where the vector begins. So we go from tail to head. The magnitude of a vector is also known as the absolute value or the length of a vector. So magnitude, absolute value, and length are synonymous. The symbol for the magnitude of a vector is the absolute value signs around the vector symbol. If we're given our vector in components here as xi plus yj, then the magnitude of our vector can be calculated by using the Pythagorean theorem approach, and will be calculated with the square root of x squared plus y squared. The horizontal component squared plus the vertical component squared, square root. Let's continue. The unit vector is defined as this symbol u with the arrow over it, and defined as being in the direction of our original vector that is 1 unit long in the same direction. We calculate our unit vector by taking our original vector and dividing it by the magnitude of our original vector, so the components. We divide the vector by its length. Two vectors are equal if they have the same magnitude and direction. So they could be anywhere on our page or in space. As long as they have the same length and are pointing in the same direction, we consider those vectors to be equal. The opposite of a vector is a vector of the same length in the opposite direction, and we simply symbolize that with a negative sign in front of our original vector. Now, a position vector is given by breaking down our vector into its horizontal and vertical components, so x times the I unit vector plus y times the j unit vector, horizontal plus vertical. Starts at the origin. A position vector starts at the origin and ends at the point x comma y. A displacement vector, on the other hand, is the difference between an object's initial and final positions. Now let's work through a couple of examples to show how two-dimensional vectors work in practice. So here's our first problem. If the vector A is 3i plus 8j, and the vector b is 4i minus 2j, we want to find the sum of the vectors a plus b. Well, that's really straightforward. We simply add our I values and get 7i, and add our j values, so 8 minus 2 is 6j. So 7i minus or plus 6j. Let's take a look at another problem. Given the same two vectors, find a minus b. Well, again, the same logic. 3 minus 4 gives me minus 1i, and 8 minus a negative 2 gives me 10j. So minus 1 plus 10. Now if we want to find the opposite of a, or negative a, we simply take our vector a, so 3I plus 8j, and we multiply the entire vector by negative 1, so we distribute, and we end up with negative 3I minus 8j. All straightforward so far. Now if we want to find 5a plus 9b, we need to follow the same order of operations that we would in standard algebra. So we'll take 3I plus 8j, multiply that by 5, distribute, so we get 15I plus 40j. Do the same thing with vector b, except multiply by 9, so 9 times 4I minus 2j, which gives me 36I minus 18j. Now we're going to add those together, so 15 plus 36 gives me 51I, and 40 minus 18 gives me 22j. And there's our answer, 51I plus 22j. Now, those absolute value bar signs here mean find the magnitude. So the first thing we need to do is add those two vectors together again, which gave us 7I plus 6j. And then to find the magnitude, we apply our Pythagorean theorem concept. So we would take 7 squared, add 6 squared, and then take the square root of that, which gives me the square root of 49 plus 36, which works out to the square root of 85. So in this case, our answer would be E. Now we're being asked to find the magnitude of A plus the magnitude of B. So find the magnitudes before we add the two pieces of information together. So the magnitude of A, by our Pythagorean property, would be the square root of 3 squared plus 8 squared, which works out to the square root of 9 plus 64, or the square root of 73. The magnitude of B is the square root of 4 squared plus negative 2 squared, which is the square root of 16 plus 4, or the square root of 20. So the magnitude of A plus B would be the square root of 73 plus the square root of 20. Now, is the magnitude of A plus the magnitude of B equal to A plus B? Well, clearly not, because the square root of 85, which we found for the magnitude of A plus B, is not equal to the square root of 73 plus the square root of 20. You can check that on your calculators if you'd like. Now, to find a unit vector in the direction of A, we have to remember the definition of a unit vector, where the unit vector is equal to our original vector divided by the magnitude of our vector. So we'll take vector A, 3I plus 8j, and divide it by the magnitude of our vector, which we remember was the square root of 73. So I can divide each of these components. So 3 over root 73 I plus 8 over root 73 j, which happens to be answer E here. Let's take a look at another problem. Find a vector of length 10 in the direction of A. Well, here, since we have a unit vector in the direction of A, and we need a vector of length 10, we can just take our unit vector of length 1 and multiply it by 10 to get a vector of length 10 in the same direction. So if we remember that our unit vector for A was 3 over root 73 I plus 8 over root 73 j. If I take that unit vector and multiply it by 10, then I will get the vector they're asking for. So that works out to be, by distribution, 30 over root 73 I plus 80 over root 73 j. And there we see that as answer D here of all our options. Now, if I want to sketch B as a position vector, we have to remember that a position vector starts at the origin. So I'm going to start at the origin here, and then I'm simply going to follow the instructions for B according to the horizontal and vertical components. So I'll step over 4 units horizontally, 1, 2, 3, 4, and then I will go down 2 units vertically, and that's where I end up, right here. So I'm going to draw my unit vector from the origin, because that's what a position vector does, and ends up at this point x comma y. And I'll put my arrow there, and there we have vector B as a position vector. Remember that I could translate that vector to anywhere in this xy plane, and it would be equal to B. But if we want it to be a position vector, it needs to start at the origin. Now, if we want to find the angle for B in standard position to the nearest tenth of a degree, we simply have to apply our right triangle trigonometry. Here's my vector B. It's going to go out 4 units and down 2 units, and I want to find the angle from standard position for this particular vector. So, since I have information about the horizontal and vertical sides, that would correspond to the opposite and adjacent of my right triangle that I have sketched here. So, to find theta, or our angle for B, I would use the arctan of the opposite over the adjacent, so negative 2 over 4, to find what that is equal to. So we'll pull out our calculator, make sure we're in degree mode, and take the inverse tangent of negative 2 divided by 4. And we get an angle of negative 26.565 degrees. But I'm going to want an angle between 0 and 360 for our vector. So I'm going to find a coterminal angle by adding 360 degrees. And find out that my angle is 333.4 degrees. Here's another example. Given the point C, 8, 25, and D, 17, 3, find the vector CD, the vector pointing from C to D. Well, let's plot those 2 points to start with. 8, 25. Let's just take our x values to be by 2's and our y values to be by 5's. So 2, 4, 6, 8, 5, 10, 15, 20, 25. That will be point C. And point D, 10, 12, 14, 16, 17, and up 3. So right about here will be point D. And we want to determine the displacement vector from C to D. So what we do is we figure out how far we have to move in the horizontal and vertical directions to get from C to D. Well, to get from C to D, I ended up at 17 and started at 8. So my I value will be 9. And I ended up at 3 and started at 25. My y values, or so in the j direction, I ended up going negative 22j. So my vector CD from C to D would be 9I minus 22j. Now, the next question is to find the position vector of the point 3/4 of the way from C to D. So if we looked at our diagram here, from C to D, about 3/4 of the way is about right here. And what I want to find is the position vector. And we know that position vectors always start at the origin. So I'm looking for this vector right here. Now, it'll be a little hard to calculate straight off, so what I'm going to do is take a roundabout path given information that I already know. So I'm going to start at the origin, and I'm going to move to point C, and then from there, from point C, I can move 3/4 of the way along my displacement vector from C to D, and end up at the location I want. So the resultant of these two vectors, vector 1 and vector 2, I'll call them, that red line is the resultant. So if I can find those two vectors and add them together, then I should get the answer to my question. Now, the first vector is just the position vector to point C. So vector 1 is going to be 8I plus 25j. That's how I get to point C, by going 8 units horizontally and 25 units vertically. Now, to find vector 2, my displacement vector, well, that's going to be 3/4 of my displacement vector that I just figured out. So 3/4 of 9I minus 22j. And to get my red vector, my new vector to that 3/4 position, I just need to add these two vectors together. And when I do that, I take 3/4 of 9, add 8, and I get 14.75I. And I take 3/4 of negative 22 and add that to 25, and I get 8.5j. And that is my position vector to that point 3/4 of the way between C and D. So there's my answer. So let's recap quickly here. What is a vector quantity? What is a scalar quantity? What is a vector? All these questions can be answered from this table. A vector quantity has both magnitude and direction. A scalar quantity has quantity but no direction. A vector, directed line segment that represents a vector quantity, and the symbol we use is that little arrow over our variable to represent a vector. The head is where the vector ends. The tail is where the vector begins. Magnitude, absolute value, length of a vector all mean the same thing. When we're talking about those three things, or that one thing, we use those absolute value bars to talk about that quantity. To calculate that quantity, we take the square root of the horizontal component squared plus the vertical component squared. Our unit vector, we typically use u to describe the unit vector, and it's in the direction of v, and it's 1 unit long. To calculate u, we take our vector and divide it by its length or its magnitude. Two vectors, again, are equal if they have the same magnitude and direction, and the opposite of a vector is a vector of the same length in the opposite direction. And we use negative v to denote that opposite vector. Position vectors start at the origin and end at the point xy, so can be written as xi plus yj. And a displacement vector is the difference between an object's initial and final positions. How do we denote a vector sum? A vector sum is we show a vector sum by connecting two vectors head to tail. How do we draw the resultant? From the tail of the first vector to the head of the second vector. How do we denote a vector difference? Well, we're really adding the opposite vector. We can think of that as a plus negative b. So instead of connecting head to tail, we actually connect tail to tail. And how do we draw the resultant of that vector difference? Well, we draw from the head of the second vector to the head of the first vector when they are connected tail to tail.